In this video, we're going to look at a few more examples of the ratio test. Test the series summation n equals 1 to infinity, negative 1 to the power of n times 3 to the power of n times n factorial, divided by 5 times 7 times 9 times 11, and so on, all the way to 2n plus 3. We're testing this series for convergence or divergence. We're going to be applying the ratio test. So let's apply the ratio test with a sub n is equal to negative 1 to the power of n times 3 to the power of n times n factorial divided by 5 times 7 times 9 times 11 all the way up to 2n plus 3. So L is equal to limit n approaches infinity, absolute value of a sub n plus 1 divided by a sub n. This is equal to limit as n approaches infinity. Now plug in n plus 1 wherever we see an n. So we have negative 1 to the power of n plus 1, 3 to the power of n plus 1, times n plus 1, factorial, divided by 5 times 7 times 9 times 11, and so on, all the way up to 2n plus 3. But we're plugging n plus 1 here. So we have 2 times n plus 1 plus 3. That gives us 2n plus 2 plus 3. That gives us 2n plus 5 as the last term. Divided by negative 1 to the power of n times 3 to the n times n factorial divided by 5 times 7 times 9 times 11 all the way up to 2n plus 3. All right, so let's simplify this. We get L is equal to limit n approaches infinity, absolute value of negative 1 to the power of n plus 1 divided by negative 1 to the power of n times 3 to the power of n plus 1 times n plus 1 factorial divided by 5 times 7 times 9 times 11 all the way up to 2n plus 3 times 2n plus 5. And let's flip this fraction, so we get 5 times 7 times 9 times 11 all the way up to 2n plus 3, which is this last term here, divided by 3 to the power of n times n factorial. Now we can simplify a little bit, so we have all of this in the numerator, of this fraction cancels with all of this in the denominator of this fraction, and simplifying it a little bit further, we get L is equal to limit n approaches infinity, absolute value of negative 1, because they have the same base, subtract off the exponents, we get negative 1 to the power of n plus 1 minus n, which is just negative 1, times 3 to the power of n plus 1, divided by 3 to the power of n, times n plus 1 factorial, which can be rewritten as n plus 1 times n factorial, divided by n factorial. So we can simplify this quite a bit. And of course, the n factorial cancels out. So we have L is equal to limit n approaches infinity. I'm going to rewrite some of the steps that we did earlier. N approaches infinity of absolute value of negative 1, 3 to the power of n plus 1, divided by 3 to the power of n. We have n plus 1 factorial, which we rewrote as n plus 1 times n factorial, divided by n factorial, and we had 5 times 7 times 9 times 11 all the way up to 2n plus 3. And in the denominator, we have 5 times 7 times 9 times 11 times all the way to 2n plus 3 times 2n plus 5. So L is equal to absolute value of negative 1 is just 1, so that's just 1 times 3 to the power of n plus 1 divided by 3 to the power of n. Same base, subtract off the exponents, so we just get 3. N plus 1 factorial cancels, and we have n plus 1. And of course, we have these cancellations. 5 times 7 times all the way to 2n plus 3 cancels with this part of the denominator of this fraction. And we get 1 over 2n plus 5. And let's put limit as n approaches infinity. So let's clean it up a bit. L is equal to limit n approaches infinity 3 times n plus 1 divided by 2n plus 5. This is equal to limit n approaches infinity 3n plus 3 divided by 2n plus 5, and divide by the highest power in the denominator, divide by n, divide by n, and divide by n. So L is equal to limit n approaches infinity 3n divided by n, that gives us 3 plus 3 over n, divided by 2 plus 5 over n. Taking a limit as n approaches infinity, 3 over n approaches 0, 5 over n similarly approaches 0 as n approaches infinity. The result is 3 over 2, which is bigger than 1, which means the series diverges. The series diverges by the ratio test. So we always have to make this statement that the series either converges or diverges by the ratio test. All right, let's look at another question. The terms of a series summation an are given by the recursive relationship a sub 1 is equal to 2, a sub n plus 1 is equal to 2n plus 1 divided by 4n minus 2 times a sub n. Determine whether the summation, the series summation n equals 1 to infinity, a sub n converges or diverges. We're going to apply the recursive relation itself to form the ratio test. Notice that we have an plus 1 divided by a sub n is equal to 2n plus 1 divided by 4n minus 2. So it's natural to apply the ratio test to solve this question. So L is equal to limit n approaches infinity, absolute value of a sub n plus 1 divided by a sub n. This is equal to limit n approaches infinity of absolute value of 2n plus 1 divided by 4n minus 2. And we don't need the absolute value because all the terms are positive. 2n plus 1 is positive, 4n minus 2 is also positive. So this is equal to limit as n approaches infinity of 2n plus 1 divided by 4n minus 2. Dividing by the dominant term in the denominator and taking the limit, this limit will be equal to 2 over 4, which is 1/2. Also, you can always apply a shortcut. Whenever you have a rational function and a numerator and denominator have equal powers of n, then the coefficients, the ratio of the coefficients is the value of the limit. So in this case, it's just 2 over 4, which is 1/2. So 1/2 is less than 1. So since L is equal to 1/2, which is less than 1, then the series summation an n equals 1 to infinity converges by the ratio test. We always have to make this statement at the end. Give the reason for which the series either converges or diverges. In this case, because the value of L was 1/2, L is equal to 1/2, which is less than 1, this series converges absolutely by the ratio test. Or you can just say converges by the ratio test. All right, let's look at another question. Test the given series, summation n equals 1 to infinity, negative 1 to the power of n plus 1, divided by e to the power of n factorial for convergence or divergence. So what we have is summation n equals 1 to infinity minus 1 to the power of n plus 1 divided by e to the power of n factorial. We're going to apply the ratio test with a sub n is equal to negative 1 to the power of n plus 1 divided by e to the n factorial. So L is equal to limit n approaches infinity, absolute value of a sub n plus 1 divided by a sub n. This is equal to limit n approaches infinity, absolute value. Now plug in n plus 1 wherever you see an n. Now this is a bit tricky because we already have negative 1 to the power of n plus 1. So we have to write this as negative 1 to the power of n plus 1 plus 1, which is n plus 2, divided by e to the power of n plus 1 factorial, all divided by negative 1 to the power of n plus 1 divided by e to the power of n factorial. Now let's simplify this. So L is equal to limit as n approaches infinity, absolute value of negative 1 to the power of n plus 2 divided by negative 1 to the power of n plus 1. Everything else is positive, so we don't need the absolute value. Simplifying this, flipping this fraction, we're going to get e to the n factorial divided by e to the power of n plus 1 factorial. So this is equal to limit n approaches infinity and negative 1 raised to the power of n plus 2 divided by negative 1 to the power of n plus 1. Subtract off the exponents because we have the same base. We get absolute value of negative 1, and we have e to the n factorial on top, and we have e to the power of n plus 1 factorial. This simplification is going to be a little bit tricky. So we have L is equal to limit as n approaches infinity. Absolute value of negative 1 is just 1. So we have e to the power of n factorial divided by e to the power of, now let's rewrite n plus 1 factorial as, no, actually let's just keep it as is, n plus 1 factorial, and subtract off the exponents. So we get limit n approaches infinity, 1 divided by e to the power of n plus 1 factorial minus n factorial. Because we have the same base, we subtract off the exponents. So L is equal to limit as n approaches infinity, 1 divided by e to the power of n plus 1 times n factorial minus n factorial. All of this is in the exponent. This is equal to limit n approaches infinity and 1 over e to the power of, now I'm going to factor out n factorial times n plus 1 minus 1. 1 minus 1 cancels out, so we get L is equal to limit n approaches infinity, 1 divided by e to the n factorial times n. And of course, this ratio will approach 0 because we have 1 divided by e to the power of n factorial times n, which grows to infinity very fast. So 1 over infinity is equal to 0. L is equal to 0, which is less than 1. So we say since L is equal to 0, the ratio L is equal to 0, less than 1. Therefore, by the ratio test, this series converges. So this series, the given series, summation, n equals 1 to infinity, negative 1 to the power of n plus 1, divided by e to the power of n factorial, converges absolutely by the ratio test. So always we have to make this statement. So we look at the value of L, and in this case, the value of L was less than 1. That means by the ratio test, the given series converges. All right, thanks.